Modern agriculture likes to believe it has already won. Bigger machines, smarter software, genetically advanced seeds, precision inputs applied down to the square meter. On paper, the system looks flawless, efficient, optimized, future-proof, and yet, in many regions, yields have plateaued, production costs keep climbing, and soils are becoming increasingly dependent on external corrections just to maintain average performance. This contradiction is not accidental. It is structural. For decades, productivity has been sold as a linear equation: more technology equals more yield. That logic worked long enough to become dogma, and once a temporary truth turns into permanent belief, it stops being questioned. The real problem is not the lack of innovation. Agriculture today has access to more data, tools, and biological knowledge than ever before. The problem is how these tools are being used, or more accurately, how they are being repeated. Modern farming has confused intensity with intelligence. Applying more inputs does not automatically mean managing the system better. Repeating a successful recipe year after year feels safe, but safety in agriculture is often an illusion created by short-term results. What worked 5 seasons ago may still produce acceptable yields today. That does not mean it is sustainable. It does not mean it is efficient. And it certainly does not mean it is preparing the system for the next decade. Soil does not operate on tradition. It responds to physics, chemistry, and biology. Every decision leaves a trace. Every shortcut has a delayed cost. And those costs rarely show up in a single season. One of the most dangerous ideas in modern agriculture is the belief that stagnation is normal. When yields stop growing, the blame is usually placed on weather, markets, or regulation. Rarely on management itself. But systems do not stall randomly. They stall when they are pushed without being understood. This illusion of productivity is comfortable. It allows producers to feel modern, efficient, and competitive, while slowly eroding the very foundation that supports production. The soil becomes a platform instead of a system. Biology becomes an afterthought. Variability is ignored in favor of standardization. And that is where the real mistake begins. Because agriculture is not failing due to lack of tools. It is failing due to lack of system-level thinking. The core mistake in modern agriculture is not a lack of effort, investment, or technology. It is the blind repetition of standardized management in systems that are anything but standard. Across regions, crops, and climates, the same pattern repeats itself. A producer finds a formula that works reasonably well. Yields are acceptable, costs are tolerable, and the operation feels stable. Instead of questioning why it worked, that formula becomes locked in. Year after year, the same fertilizer rates, the same timing, the same crop sequence, the same logic. The system stops being managed and starts being replayed. This mistake feels rational. Agriculture is risky, and repetition feels like control. But repetition without feedback is not control. It is inertia. The land changes every season. Organic matter shifts. Microbial populations respond. Compaction builds or relieves. Nutrient cycling accelerates or stalls. Climate variability adds another layer of complexity. None of these variables care about last year's spreadsheet. Yet modern management often treats fields as static units. Soil tests become formalities. Prescriptions are copied forward. Variability is averaged out because averages are easier to manage than reality. The result is a system optimized for convenience, not performance. One of the most damaging assumptions in agriculture is the idea that close enough is good enough. If yields are within an acceptable range, the system is considered healthy. But acceptable yields can hide declining efficiency. They can mask increasing dependency on inputs. They can conceal biological collapse beneath chemical compensation. This is how systems quietly degrade. When productivity depends more on correction than on function, the system is already in trouble. More nitrogen is applied to compensate for poor mineralization. More fungicide is used to offset weak plant health. More fuel is burned to manage compaction that should not exist in the first place. Each correction solves a symptom while reinforcing the underlying problem. Standardized management also ignores one of agriculture's most uncomfortable truths. Variability is not the enemy. Misunderstood variability is. Fields are not uniform, never were, never will be. Treating them as such forces managers to aim for the middle, which means overapplying in some areas and underperforming in others. The system becomes inefficient by design. The irony is brutal. Precision agriculture exists to manage variability, yet many operations use it only to apply the same logic more accurately. Technology becomes a delivery mechanism for old habits. The core mistake, then, is not copying others. It is copying without context, without diagnosis, without system awareness. High-performing agricultural systems are not built on recipes. They are built on feedback loops: observation, adjustment, and response. When those loops are broken, repetition takes over. And repetition feels productive until the bill arrives. That bill does not come all at once. It shows up as tighter margins, more volatility, higher sensitivity to stress, less resilience when conditions turn unfavorable. And by the time it becomes obvious, the system is already fragile. This is not a failure of farmers. It is a failure of how agriculture has been taught to think. Manage inputs, control outcomes, repeat success. But agriculture does not reward repetition. It rewards adaptation. And adaptation starts with understanding the system, not memorizing the recipe. To understand why repetition dominates modern agriculture, it helps to look at how the system was trained to think. This did not happen overnight, and it did not happen by accident. For decades, agricultural success was built around simplification. Complex biological systems were reduced to manageable variables: nitrogen, phosphorus, potassium, plant population, planting date, spray schedule. This reduction was necessary at the time. It allowed agriculture to scale. It allowed knowledge to spread quickly. And for a long period, it worked. The problem is that simplification slowly turned into rigidity. As farms grew larger, decision-making had to become faster. Advisors needed recommendations that could be applied across hundreds or thousands of hectares. Input companies needed clear protocols. Universities needed models that could be replicated and taught efficiently. The result was a system that rewarded uniformity over nuance. Producers were not trained to read systems. They were trained to follow programs. This created a subtle but powerful shift in mindset. Instead of asking, "What does this field need this year?" the dominant question became, "What is the recommended rate?" Instead of observing soil behavior, producers learned to trust averages. Instead of feedback, they learned compliance. Over time, repetition became a signal of professionalism. Changing management too often looked risky. Deviating from standard recommendations felt irresponsible. Stability was confused with competence. The advisory structure reinforced this behavior. Many recommendations were built around products, not processes. If yields dropped, the response was rarely to reduce intervention or rethink system design. The response was to add another layer, another application, another input. Each layer made the system more complex, but not necessarily more intelligent. This training also created a dangerous dependency. When decisions are outsourced to programs and prescriptions, understanding erodes. The producer becomes an operator of instructions rather than a manager of systems. When conditions change, the playbook no longer fits, and adaptation becomes slow and uncertain. What makes this especially problematic is that agriculture now operates in a far more volatile environment than when these models were created. Climate variability is higher. Input costs fluctuate wildly. Soil degradation has accumulated over decades. Biological resilience matters more than ever. Yet the decision-making framework remains largely the same. The industry still pushes stability in a world that demands flexibility. Repetition is comfortable because it reduces cognitive load. It limits uncertainty. It allows decisions to be made quickly. But comfort in agriculture is expensive. It costs efficiency. It costs resilience. And eventually, it costs profitability. The systems that perform best under stress are not the most controlled ones. They are the ones that were designed to respond. Agriculture was trained to repeat because repetition once delivered growth. That historical success makes it hard to abandon. But systems evolve, context shifts, and methods that once scaled productivity can later constrain it. The challenge now is not learning more products or more techniques. It is unlearning the belief that consistency alone creates success. Because consistency without understanding is just habit. And habits do not adapt. Soil is the most managed and least understood component of modern agriculture. It is sampled, corrected, fertilized, sprayed, compacted, and driven over, yet rarely observed as a living system. Most management decisions treat soil as a static medium, a platform that holds roots and delivers nutrients on demand. That assumption is convenient. It makes planning easier. It turns complexity into numbers. But it is also deeply flawed. Soil is not an inert container. It is a dynamic system governed by physical structure, chemical balance, and biological activity. These three components interact constantly, and weakening one inevitably stresses the others. When management focuses exclusively on chemical correction, physical degradation and biological collapse often follow quietly. One of the biggest blind spots in modern agriculture is the separation of soil fertility from soil function. Nutrient levels can be optimal on paper while the system itself struggles to deliver those nutrients to plants. Compaction restricts root growth, poor aggregation limits oxygen exchange, low biological diversity reduces nutrient cycling efficiency. In those conditions, more fertilizer does not solve the problem. It masks it. Plants growing in dysfunctional soils are forced into dependency. Their roots explore less volume. Their access to water becomes inconsistent. Their interaction with microbes weakens. Stress tolerance drops. Yield potential becomes fragile, easily disrupted by heat, drought, or disease pressure. This is why two fields with identical soil test results can perform dramatically differently. The difference is not in the chemistry alone. It is in the system. Modern management often overlooks this because system health is harder to measure than nutrient concentration. Biological processes do not fit neatly into spreadsheets. They respond to time, diversity, residue, and disturbance. They require patience, observation, and restraint. And restraint is not a trait the industry has historically rewarded. Intensive tillage, narrow rotations, and constant chemical intervention simplify soil biology. They create predictable short-term responses at the cost of long-term function. The system becomes faster but weaker, more responsive but less resilient. When stress hits, whether climatic or economic, these systems collapse faster because they lack buffering capacity. There is no biological reserve to stabilize nutrient flow, no structure to retain moisture, no diversity to absorb shocks. The tragedy is that this degradation often goes unnoticed until recovery becomes expensive. Yields may remain acceptable while efficiency declines. Input use increases to compensate. Margins shrink quietly. Producers then assume the solution is better products or more precise applications. Rarely do they step back and question whether the soil itself is still functioning as a system. Healthy soils do not eliminate the need for inputs. They amplify their effectiveness. They reduce volatility. They create margin through efficiency rather than volume. But seeing soil as a system requires a different mindset. It requires moving beyond numbers and into processes, beyond correction and into function. And until that shift happens, management will continue to treat symptoms while ignoring causes. The most dangerous costs in agriculture are not the ones that appear on invoices. They are the ones that accumulate quietly, season after season, hidden behind acceptable yields and familiar routines. By the time they become visible, they are no longer easy to reverse. When systems rely on repetition rather than adaptation, inefficiencies compound. Each year requires slightly more input to achieve the same result. Fertilizer rates creep upward, crop protection programs expand, fuel use increases, labor pressure grows. None of these changes seem dramatic on their own, but together they reshape the cost structure of the operation. This is how profitability erodes without a clear moment of failure. One of the most overlooked hidden costs is lost efficiency. Nutrients applied but not utilized. Water available but not accessed. Genetic potential limited by root environment. These losses rarely show up as total failure. They show up as ceilings. Yield plateaus that refuse to move, no matter how much is invested. Producers often respond by pushing harder against that ceiling. More inputs, more passes, more complexity. The system becomes heavier, not smarter. Another hidden cost is risk exposure. Simplified systems are fragile. When management relies on narrow margins of timing and performance, any disruption becomes expensive. A delayed application, an unexpected weather event, a supply chain issue. What once caused minor inconvenience now threatens the entire season. Over time, this fragility forces conservative decisions. Innovation slows. Experimentation disappears. The operation becomes defensive rather than strategic. Survival replaces optimization. There is also a biological debt being paid. Degraded structure reduces infiltration, increasing runoff and erosion. Simplified biology slows nutrient cycling, increasing dependency on synthetic inputs. Compaction restricts rooting depth, reducing drought tolerance. These are not theoretical concerns. They directly affect yield stability. The cost of rebuilding these systems is always higher than the cost of maintaining them. Restoring structure, rebuilding organic matter, re-establishing biological diversity. These processes take time and discipline. They do not respond to emergency spending. What makes this especially frustrating is that many of these costs are avoidable. They are not the result of bad luck or uncontrollable variables. They are the predictable outcome of managing complex systems with static logic. High-performing agricultural systems are not necessarily the highest input systems. They are the most efficient ones. They convert investment into output with minimal waste. They respond to stress without collapsing. They protect margin by reducing volatility. The hidden cost of repetition is not just money. It is lost optionality. Once a system becomes heavy and dependent, choices narrow. Management flexibility disappears. The operation becomes locked into its own past decisions. This is why the most successful producers obsess over efficiency rather than yield alone. Yield is a result. Efficiency is a strategy, and strategies that ignore long-term system cost always fail eventually. Technology was supposed to make agriculture smarter. In many cases, it did. But in just as many, it simply made bad logic more efficient. Modern farms are full of advanced tools. Yield monitors, variable rate application, satellite imagery, sensors, automation, artificial intelligence. The problem is not the absence of technology. The problem is the mindset guiding its use. Too often, technology is treated as a solution rather than a diagnostic. Precision tools are frequently deployed to execute the same management decisions with greater accuracy. The same rates, the same timings, the same assumptions, just delivered more precisely. This feels progressive, but it changes very little at the system level. Applying the wrong decision perfectly does not make it right. Many operations collect enormous amounts of data and do almost nothing with it. Maps are generated, stored, and forgotten. Variability is visualized but not interrogated. Instead of asking why a zone underperforms, it is averaged out or compensated with higher inputs. Technology becomes a way to avoid uncomfortable questions. The real power of modern tools lies in feedback. They reveal patterns, stress points, inefficiencies, and system failures. But feedback only matters if it drives change. When data is used to confirm existing beliefs rather than challenge them, it loses its value. Another common mistake is chasing resolution instead of relevance. Finer grids, more layers, more sensors. Meanwhile, the core management logic remains unchanged. The system gets more detailed but not more adaptive. This obsession with tools can also create dependency. When decision-making is outsourced to software defaults and algorithms, understanding erodes further. Operators follow prescriptions without knowing the underlying assumptions. When conditions fall outside the model, the response is confusion rather than adjustment. Technology should reduce uncertainty, not replace thinking. High-performing systems use technology to ask better questions, not to automate habits. They use it to identify limiting factors, test hypotheses, and refine management over time. Data becomes part of a learning loop, not a reporting exercise. When technology is aligned with system thinking, it amplifies intelligence. When it is layered onto repetition, it amplifies waste. The difference is not the tool. It is the intent behind its use. When performance stalls, the instinctive response in agriculture is to add more. More fertilizer, more protection, more passes, more cost. This response feels logical because inputs are tangible. They can be measured, purchased, applied. They give the impression of action. But adding inputs to a dysfunctional system does not fix it. It only increases dependency. Inputs are designed to support function, not replace it. When soil structure limits root growth, extra nutrients cannot compensate. When biological activity is weak, chemical availability does not translate into uptake. When water movement is restricted, yield potential collapses regardless of how much is applied. This is where the myth of control breaks down. Modern agriculture often treats inputs as levers that directly control output. Pull the lever harder, get more yield. In reality, inputs work through systems. If the system is constrained, the response is muted or inconsistent. This leads to diminishing returns. Each additional unit of input delivers less benefit than the previous one. Margins shrink while risk increases. The operation becomes heavier, slower, and more fragile. Worse, excessive inputs can actively harm system function. High salt loads stress biology. Overapplication disrupts nutrient balance. Aggressive chemical programs reduce microbial diversity. Short-term gains are purchased with long-term damage. This cycle creates a dangerous illusion. When yields hold steady despite rising inputs, the system appears stable. In reality, it is being artificially supported. Like a patient on life support, performance depends on constant intervention. The moment intervention is reduced, collapse follows. High-performance systems behave differently. They respond strongly to small adjustments. They convert modest inputs into reliable output. They recover quickly from stress. Their productivity is rooted in function, not force. This is why producers who focus solely on input optimization often miss the bigger picture. Efficiency is not about using less. It is about getting more response from what is used. More inputs do not fix broken systems. They hide the cracks, and systems that rely on hiding cracks always fail under pressure. High-performance farmers are often misunderstood. From the outside, their operations may not look radically different. They use modern equipment, they apply inputs, they manage risk. The difference is not what they use. It is how they think. These producers do not manage for averages. They manage for response. Instead of asking how much input to apply, they ask what is limiting performance. Instead of copying recommendations, they observe behavior. Fields are not treated as uniform units but as collections of systems with different constraints. They pay close attention to feedback. Yield maps are not just records. They are questions. Soil tests are not prescriptions. They are signals. Crop performance is interpreted in context, not isolation. This mindset changes everything. High-performance systems are built around flexibility. Management decisions are adjusted annually, sometimes seasonally. Rotation is used strategically, not just operationally. Diversity is introduced deliberately to create biological leverage. These producers are not chasing maximum yield at any cost. They are chasing consistency, resilience, and efficiency. Yield becomes a consequence, not the goal. Another key difference is restraint. High-performance farmers know when not to act. They avoid unnecessary disturbance. They resist the urge to correct every fluctuation. They understand that systems need time to respond and stabilize. This restraint is often mistaken for passivity. In reality, it requires confidence and deep understanding. They also experiment, but with structure. Small-scale trials, side-by-side comparisons, controlled changes. Learning is intentional. Failure is contained. Success is scaled. Technology, in these systems, is a diagnostic tool. It is used to identify patterns and refine decisions, not to automate routines. Data informs strategy rather than replacing it. Perhaps most importantly, high-performance farmers think in timelines longer than a single season. Decisions are evaluated based on their impact across multiple years. Soil function, not just yield, becomes a performance metric. This long-term perspective creates an advantage that compounds over time. Systems become easier to manage, not harder. Variability becomes manageable rather than threatening. Margins stabilize even when conditions are unfavorable. These operations are not immune to stress. They are simply prepared for it. And preparation, in agriculture, is the true competitive edge. One of the most difficult transitions in modern agriculture is moving away from product-centered thinking. For decades, management has been organized around packages. Fertility programs, protection programs, seed programs, each designed to solve a specific problem in isolation. This approach is efficient for selling solutions. It is inefficient for managing systems. System thinking requires a fundamental shift. Instead of asking which product to use, the question becomes why the problem exists in the first place. Instead of stacking solutions, managers begin redesigning processes. This is uncomfortable because it removes certainty. Packages come with instructions. Systems demand judgment. In a system-driven operation, inputs are tools, not crutches. They are selected based on context, timing, and interaction, not tradition. Decisions are evaluated by their downstream effects, not just immediate response. This shift also changes how success is measured. Short-term yield spikes become less important than long-term stability. Reduced variability matters more than peak performance. Soil resilience becomes as valuable as output volume. System thinkers accept complexity rather than fighting it. They understand that agriculture is not linear. Small changes can have disproportionate effects. Interventions interact, outcomes emerge rather than being fully controlled. This perspective transforms management from execution to strategy. Product-driven systems are reactive. Problems appear and solutions are applied. System-driven operations are proactive. Design choices reduce the likelihood and severity of problems before they appear. This does not eliminate risk. It redistributes it. Instead of relying on constant correction, risk is absorbed by biological and structural resilience. The hardest part of this transition is letting go of false certainty. A recipe feels safe, a system feels uncertain, but certainty based on incomplete understanding is fragile. Uncertainty managed through observation and adaptation is robust. The future of agriculture does not belong to those who apply the best packages. It belongs to those who design the best systems. One of the greatest misunderstandings in modern agriculture is the belief that variability is a flaw to be eliminated. Uneven yields, different soil behaviors, inconsistent crop responses. These are treated as problems to be corrected, flattened, neutralized. But variability is not the enemy. Mismanaged variability is. Every field contains multiple systems operating simultaneously. Differences in texture, organic matter, topography, water flow, and biological activity create natural variation. This variation is information. It reveals how the system responds under different conditions. When management ignores this information, it wastes potential. Many operations attempt to force uniformity through aggressive correction. More fertilizer in weak zones. More chemistry where pressure appears. More intervention to make the map look prettier. This approach treats symptoms, not causes. High-functioning systems use variability as a guide. They identify limiting factors instead of compensating blindly. They allow strong zones to express their potential and focus effort where response is possible. Flattening variability does not increase performance. Understanding it does. The most efficient systems are not uniform. They are intentional. Resilience is often marketed as a product, a treatment, a technology, something that can be applied when conditions become difficult. This framing is misleading. Resilience is an emergent property of system design. A resilient agricultural system does not avoid stress. It absorbs it, it bends without breaking. This capacity is not created by emergency intervention. It is built gradually through structure, diversity, and function. Soil aggregation improves water infiltration. Biological diversity stabilizes nutrient cycling. Root depth buffers drought. Rotation disrupts pest and disease cycles. None of these effects are instant. All of them compound over time. Buying resilience is impossible. Designing for it is not. Systems that rely on constant correction appear strong in favorable years. Under stress, they collapse faster because they lack internal buffering. Systems designed for resilience may not always maximize short-term yield, but they maintain performance when conditions deteriorate. In modern agriculture, resilience is margin protection. Scale does not create problems. It magnifies them. When management logic is sound, scale amplifies efficiency. When logic is flawed, scale accelerates failure. Small inefficiencies become massive costs. Minor system weaknesses become structural risks. This is why repetition becomes especially dangerous at scale. A mistake applied once is a lesson. A mistake applied across thousands of hectares is a liability. Large operations require simplicity, but simplicity must come from design, not denial. Ignoring complexity does not remove it. It only postpones the consequences. The most successful large-scale systems are not simplistic. They are modular. They allow variation within structure. They decentralize decision-making while maintaining strategic coherence. Scale rewards clarity of thinking. It punishes lazy logic. The most expensive decision in agriculture is often not action, but delay. Systems rarely fail suddenly. They signal stress long before collapse. Declining response, narrower margins, increasing volatility. These signals are easy to ignore when yields remain acceptable. Waiting feels safe. It is not. The longer a system operates in degradation, the more expensive recovery becomes. Biological rebuilding takes time. Structural repair requires restraint. Lost optionality cannot be purchased back quickly. Producers who adapt early pay less. They adjust gradually. Those who wait are forced into abrupt change under pressure. In agriculture, timing is not just agronomic. It is strategic. The next competitive advantage in agriculture will not come from a new product category or a breakthrough machine. It will come from the ability to manage systems holistically under uncertainty. Producers who understand feedback, variability, and long-term dynamics will outperform those who rely on repetition and force. Not because they work harder, but because their systems work with them. The future will reward clarity over complexity, design over reaction, and understanding over habit. Agriculture has never been about control. It has always been about response. Those who learn to respond well will not just survive. They will lead.